Our next speaker is Štrancar, Managing Director at Sartorius, and the title of his talk is Manufacturing of LNPs with Multiple Nucleic Acid Payloads. Alice?
Is the microphone working? Okay, I hear something. Okay, so welcome to everybody in the last day of this event. I will try to give you a bit of insights to the LNPs, how to make them, how to analyze them. We see lately that LNPs are becoming more and more important delivery systems. And before going to the LNP, very shortly about our products portfolio, how to run the manufacturing of the LNPs, which are loaded with the nucleic acids, about two-dimensional LNP and why it is good for, and how to produce LNPs to still make them stable, not to kill them by shears, and in the end of the story, a bit of future. Where are we going with this stuff? Before going to the details, so I'm an analytical chemist, and believe me, do not trust to analytics. Therefore, if you would really like not to be misled, and I have been many times misled in my more than 30 years career, almost 35 years in the biomanufacturing, so many failures because we didn't have good analytics or we didn't understand the analytics. So very important, use orthogonal methods. Maybe not only two, sometimes even three, to really understand what is going on. And do not start to develop your process unless you have at least two good analytical methods in your hands. Otherwise, you'll probably make a lot of mistakes, and your process development might take years instead of months. And yes, the PET-fix systems which we build it is actually to help with at least one of such analytical methods with one orthogonality. The company, we are now 27 years old. We are located in Slovenia, which is a very small country in the middle of Europe, a valley with very, very strong wind, can be 150 miles per hour, but we are still okay. Nothing blows away. We know how to build houses for such strong wind. But this strong wind is very good for very good wines, and especially for very good prosciutto. And hopefully nobody is here from Italy, not to fight with me. There is one, okay. Good. Since very beginning, we were in gene therapy, so working with nucleic acids for many years, and also viral particles. And because we know particles, we are now able to study the LNPs as well, because for us, LNP is just one of the particles. End of 2020, we have been acquired by Sartorius, so we still try to keep quite independent. This gives us flexibility to develop processes and products faster than it would be the case in bigger company. The first product we started with close to 30 years ago are monolithic columns. Why monolithic columns? These are columns which only have channels through the resin, a laminar flow, no diffusivity constraints, so separation can be fast. But more importantly, there is just laminar flow through. Laminar flow means no shears, no mixing, and this improves the recovery. At the time with viral particles, nowadays also with LNPs. We produce small columns, and then we go with very big ones. So we can really supply everything what you need for your manufacturing. At the moment, the 40-liter column is the biggest one, which we can provide. What else to say? You can get them also in the formats of 96 swell plates, dog-tet, like RoboColumn. The second family are our PET-fix systems, it is kind of chromatography-based system dedicated for the work. The advantage of this system is, as soon as we have method which is for analytics, we can linearly scale it up to the manufacturing. And yeah, being for a long time in the market, we gain quite some knowledge, so we can help customers to develop their processes. One of the most known processes which we co-developed is the Zolgensma. So the downstream process was co-developed in our labs. Very nice work and cooperation with the Avexis team at the time, now Novartis. Arcturus forced us about 10 years ago to start to develop oligo-DT columns. And as we have process in places, we could help with some companies to basically manufacture the COVID vaccines, especially in Asia. Yeah, the COVID vaccine or any LNP mRNA particle would start with the production, usually with the production of the DNA, either E. coli or synthetically, which means you first need to have a method to quantify the pDNA and also to quantify the pDNA. Impurities in the pDNA are causing a lot of troubles, are resulting in double-strand RNA. Residual proteins will also mess up with the purity of mRNA later on, so very important, first of all, to have good analytics and to produce pure plasmid, either nano, plasmid, mini circle, mini string, or whatever. Then we go to the mRNA, again, methods to quantify mRNA, to check for the purity, and also to have a method to optimize the mRNA. And then we also go to the LNP. So within our PET-fix, these methods are already loaded on. You get them with the system. They are validated in our labs. You also get standards. So we are very fast in starting with your own analytics. Usually within 2 weeks, you're ready to run your pDNA purity. If you look to the process, usually we would start with E. coli. If one is interested in huge manufacturing of the plasmid, you might be interested in doing continuous manufacturing. For this, we developed continuous lysis system. We call it alkalizator. And then we go to the purification steps. So first the plasmid, and then later on with the mRNA. So for all of this, we have preparative columns, but we also have PET-fix, which allows us to basically quantify the purity or quantify the impurity profile and the material with our PET-fix methods. And now going to two-dimensional PET-fix. So the LNP particle would be usually having some payloads. At the beginning, it was just one. Nowadays, we see 2, even 3 payloads. And more, you also see decoration on the surface. Quite complex sample. So what we do, we basically know that the OH column, which is kind of hydrophilic column, can basically separate particles by size. What we do here, we load the material on the OH column. Whatever is not a particle would be in the flow through. So OH column. Then we go through the valve to the inline dilution, through the Maltz detector, and on the second column where we quantify non-binded RNA, or maybe also some proteins in addition, with either US detector, also the lipids with the CUT detector. After this, we elute the material from which bind it, so the particles from the OH column, by running to the buffer water, maybe sometimes with a bit of organic solvent. We repeat again, we go to the Maltz detector, so any particle going to the Maltz detector, we would see on the Maltz detector. And then we go to the SDVB column with organic solvent, higher temperature. We disrupt the particle to the building blocks so we can measure the encapsulated RNA or pDNA. So this is the chromatogram. The upper one, I don't know why this is not really working. just a bit. So the upper one, the red, is the UV. So as I said, first the mRNA goes out, and then we would see it on the stereoantigen column. We can quantify the amount, so either the height or the area represents free mRNA. Then we elute the particles. The particles goes through the multi-light scattering detector, the detector which is basically connected immediately after UV detector. So the height of the peak would represent the amount of LNPs, and then we disrupt, the particle goes again to the SWB column, and we can measure the encapsulated RNA in this case. So if we go into the detail of the multi-light scattering peak, we can basically, due to the 9 channels on the multi-light scattering detector, also measure the size. And we can see that in the tailing, the size of the particle would be higher. We can compare now the size which we measured with multi-light scattering detector online with the nano-tracking analysis, and we can see that there is relatively good correlation between the size measured by multi-light scattering detector and by nano-tracking analysis. We also compared the encapsulation in this case, and there is a quite good correlation between ribogreen and the quantification of the encapsulation measured by the PET-fix. Yeah, this is relatively nice, relatively simple, but we have cases where we would like to basically load 2 different RNA. In this case, it was one of 1 kilobase pair, one of 4 kilobase pair. If you just look on the encapsulation, there is almost no free RNA, and both RNAs seems to be nicely encapsulated. But if you look to the LNP elution from the column, we see very big heterogeneity, which means you may have, by ribogreen, very good data about your LNP formulation, but you may not have really homogeneous product. So this is, in addition, what the PET-fix can add to the existing method to really measure heterogeneity of your stuff. Let's go further. Be careful with your lipids. Buy them really pure and make sure they are not oxidized. Oxidized lipids are by themselves mutagenic, and they basically like to make a covalent bridge with the RNA. So we talk about so-called lipidated RNA impurities, and we can measure them. They would come with our method after the encapsulated RNA. So all these peaks here, small ones, represents lipidated adducts, and I would suggest make sure you don't have them in your product. Let's go further. As I mentioned, nowadays one would like to have 2 payloads, either the plasmid and the RNA, or 2 different RNAs in the LNP. Another example, in this case, the LNP synthesis was not really going that nice. The encapsulation was not so high. And with this method, we can not only basically quantify the encapsulated material, but we could also separate the 2 RNA molecules, or actually plasmid and RNA. And if there would be degradation of RNA and plasmid, especially of RNA, we could see the leading peak here and the leading peak here, so we can also access if there is some degradation of the material. So heterogeneity, RNA lipid adducts, in this case, they were relatively okay, and RNA fragmentation. CRISPR-Cas, another story. So that's guided RNA, and that's Cas9 RNA. This one seems to be quite heterogeneous. We really didn't want to go too much into the detail. That was a customer sample. But yes, it looks not to be really pure, or maybe already partially degraded, and huge amount of lipidated RNA adducts. and then we go to the manufacturing, as already mentioned. So it is relatively easy to go from analytics to the prep. We just need bigger column, bigger pump, and how the LNP is synthesized. So usually we would have a lipid mix, which we would encapsulate with the payload in a kind of mixer. This mixer usually is quite turbulent. And this may be, especially with bigger RNA molecules, already an issue here. Instead of having just one single RNA, you may already disrupt a bit of RNA. So we are working here on something which would be purely laminar mixing. We go ahead, and then instead of TFF, which is also causing shears, we would go with just inline dilution, adding buffer. Usually this would be citric buffer of about 0.3 to 0.5 citrate, 0.5 molar citrate. This basically allows to bind any particle, and all the free stuff like RNA, like free pDNA, like non-covalently attached proteins would be in the flow-through. And then with linear gradient, we would be eluting from this column different species. The LNP may not be only one species, may be extremely heterogeneous. One of the example here, so this is the chromatogram. That's the elution, nice elution peak here, but there is a bit of material before. If you do zoom in, we see that the peak is also, that peak is here. And if you look on the picture, we see that there are bigger and smaller particles. So it's not that straightforward that we really have one nice LNP, even if you just look at things under the SEM microscope. So we collected fractions. So again, zoom in. Fraction E1, which looks to be impurity, E4, where we have the highest signal, and then E5, E6, which is a tailing. And we compare to the expression. So in E1, we have some expression, but relatively low. So where the product is the E4, it's a nice expression, the highest one, but also in the E6, there is expression. But these are different sizes of particles. So the size of this particle here is smaller than this one, and this one is bigger than this one. So we separate it by size on this column. So this is now the size of this particle. So we also see that bigger the size of the particle, later it would elute from our first column. And what to do now with this peak? Is this homogeneous? No, it is not. We need to do some further work with second dimension chromatography to really have very pure material at the end. Lately, people would like to put proteins or peptides or whatever on the surface to do kind of directed LNP. And this is causing another complexity in the manufacturing and also in the analytics. We started to develop also methods here. As I said, before we do the prep, we first tried to develop the methods, analytical methods. And with the same column, we are able to separate the free protein away from the particle without the protein on the surface and targeted LNP. So we have a method which allows us to separate targeted LNP from the untargeted LNP. Going further, depending on what the protein on the surface is, we may be using affinity chromatography, again, to further pull the stuff. So in this case, we can see on the Mal's detector targeting LNP. This is binding on the column, on the affinity column, and not really surface decorated, or the LNP without the protein covalently attached to is in the flow-through. So we can separate those LNPs which either would not have any more the active protein on the surface, or those which have no protein on the surface, from the product or from the products. And now we go further what these products are. And if I start to talk about what is then with this particle in the blood. That's really very much interested. We are starting to study corona because particles in the blood do not behave the same as in the buffer system. Neither they are stable the same in the blood as in the buffer system. So we need analytics. Once again, to conclude, no robust bioprocess without good analytics. In the bioproducts field, we really need orthogonal methods to better understand what's going on and not to be kind of tricked with wrong analytical data. LNP switcher is an orthogonal method to ribogreen. It is an orthogonal to NTA video drop, but provides you so many more data like amount of lipidated material, heterogeneity, and so on. If you compare the recovery of a bit more complex LNP with the TFF, usually TFF would result in not really better than 50% recovery. With the chromatography, you can easily reach more than 90% recovery. And chromatography purification gives high control over the entire process and allows for full scalability. With this, once again, do not trust analytics. You need orthogonal analytics to really understand your processes, and do have analytical methods in place, verified before you start to do the process development. With this, I would like you to thank you for your attention, and if there are any further questions, more than happy to revert.
Just a reminder, we have a mic in the middle for questions.
Hey, thanks for your great talk. Can you go back to the co-encapsulated LNP chromatogram? I just wonder, like on your top figure, is that like the guide RNA and mRNA LNP like loaded in different LNPs with different size?
It would be this one.
Maybe one more before this.
This one.
Yeah. So on the upper one.
This was mixed all together. So one would believe that once you mix the guided RNA and Cas9 RNA together with the lipids, that you get one particle.
Right. So I am just curious why, like, the elution time for the encapsulated guide RNA and Cas9 are like eluted at different time.
This is reverse phase chromatography, so it is kind of separation by size of the RNA. So we attach or we bind the RNA of different size, and then by elution with organic solvent we can separate them by size. This is why we can get small guided RNA to be separated from the bigger Cas9.
Can you differentiate, like, let's say for the first peak, right, the encapsulated guide RNA, are they like co-loaded with the Cas9?
I would say that probably there is some degradation, or maybe the guided RNA was not pure.
Okay. Okay, sure, thanks.
All right, thank you. It's never bad to start our coffee break a few minutes early, so thank you again. We'll reconvene at 11:15. Thank you.